Welcome all to the online lecture series on applied electromagnetic theory. In this lecture, I'll be dealing the topics from the first module. Myself, Rinju Mariam Raleigh, Assistant Professor, Department of EC, Rajagiri School of Engineering and Technology. This video lecture will help you to understand the topics continuity equation, capacitance of two-way transmission line and capacitance of coaxial cable. The prerequisites needed are vector calculus, electric field intensity, divergence theorem, and Gauss's law. Continuity equation. Continuity equation is derived from the principle of conservation of charge. And by the principle of charge conservation, the time rate of decrease of charge within a given volume must be equal to the net outward current flow through the closed surface. So by that, we can write the net outward current flow, I out, in terms of current density, that's equal to closed integral 0 ds, that's equal to the time rate of decrease of charge, that's equal to minus d by dt of q in, where q in represents the total charge enclosed by the closed surface. And for a positive value of net outward current, the enclosed charge volume should decrease with time as required by the negative time derivative. Now let's look on to the first equation. I out is equal to closed integral z dot ds, that's equal to minus d by dt of enclosed charge. Let's apply divergence theorem to the middle term of the first equation. That is, by applying divergence theorem, so closed integral j dot ds is equal to volume integral del dot j dv. Now let's take the next term, that is minus d by dt of q in. We have minus d by dt of q in. Here q in represents the charge enclosed. This charge enclosed we can represent in terms of volume charge density. That's equal to minus d by dt of volume integral rho v dv. This is equal to minus of volume integral dou by dou t of rho v dv. Here rho v, it can be a function of both space coordinates and time. That's why we have taken the partial differentiation with respect to time. So substituting equation number 2 and equation number 3 in equation number 1, we will get surface closed integral j dot ds, that is same as volume integral j dot del dot j dv, that's equal to minus d by dt of q in is same as minus volume integral dou by dou t of rho v dv. So we have volume integral del dot j dv is equal to minus of volume integral dou by dou t of rho v dv. That's equal to del dot j is equal to minus of dou by dou t rho v. And this is called the continuity of current equation or continuity equation. And continuity equation, as I already said, it is derived from the principle of conservation of charge, and it states that there can be no accumulation of charge at any point when current is flowing in a circuit. So there cannot be any accumulation of charge when current is flowing in a circuit. For steady currents or for constant current, dou by dot of rho v is equal to 0. Hence, del dot j is also equal to 0. So this means the total charge leaving a volume is same as the charge entering it. And the Kirchhoff's current law is followed from this. So keep in mind where rho v represents the volume charge density and j is the current density. Now let's consider a case of introducing a charge at some interior point of a given material, and that material can be a conductor or it can be a dielectric. And now let's refresh the basic equations of Ohm's law and Gauss's law. So from Ohm's law we know J equal to sigma E, and Gauss's law says del dot E is equal to rho V by epsilon. Substituting Ohm's law, Gauss's law in the continuity equation, we get del dot J is equal to del dot sigma E, that's is equal to sigma rho V by epsilon is equal to minus dou by dou T rho V. Just rewriting this, we get it like dou by dou T rho V plus sigma rho V by epsilon is equal to 0. So this is like a homogeneous linear ordinary differential equation. So by the variable separable method applied in equation number 6, we get dou rho V by rho V is equal to minus sigma by epsilon dou T. And integrating this equation on both sides will result in the expression ln rho V is equal to minus sigma T by epsilon plus ln rho V 0, where rho V 0 is the constant of integration. Then we can arrange the terms ln rho V here and ln rho V 0 here, so that will simplify the equation as ln rho V by rho V 0 is equal to minus sigma T by epsilon. That means rho V is equal to rho V 0 into e raised to minus sigma T by epsilon. So same we can write it like, simplify it as rho V is equal to rho V 0 e raised to minus T by TR, where TR is a time constant in seconds and the value of TR is equal to epsilon by sigma. And TR is also called relaxation time or rearrangement time. So in this expression, rho V is the volume charge density, rho V0 is the initial charge density, that is the value of rho V at time t equal to 0, and TR represents the relaxation time. The equation implies introduction of charge at some interior point of the material results in a decay of volume charge density, that is rho V. That's very clear from this expression. That is rho V, it is decaying exponentially. And along with the decay, the charge moves from the interior point at which it was introduced to the surface of the material. And relaxation time means it is the time it takes for a charge placed in the interior of a material to decay up to 36.8% of its initial value. And relaxation time, it will be short for good conductors and it will be long for good dielectrics. So let's consider two examples. Let's consider two cases where copper, that's a case for a good conductor, and a fused quartz. So for copper, the value of sigma is equal to 5.8 into 10 raised to 7 moles per meter. Epsilon r is equal to 1. And we know the expression for relaxation time TR, that is equal to epsilon by sigma. Here epsilon is equal to epsilon r, epsilon 0 by sigma. Substituting the values, epsilon 0 into epsilon r by sigma, we get 1.53 into 10 raised to minus 19 seconds. That means there is a rapid decay of charge that is placed inside the copper. Now let's consider the second case of a fused quartz, where sigma is 10 raised to minus 17 moles per meter, epsilon r is 5. Then relaxation time, that's equal to epsilon by sigma, that's equal to epsilon r, epsilon 0 by sigma. Epsilon 0 into epsilon r divided by sigma, that makes is equal to 51.2 days. That means for a good dielectric, the relaxation time is large, or we can consider a charge that is placed inside a dielectric, it will remain there forever. Capacitance. What is a capacitor? To have a capacitor, we must have two or more conductors carrying equal but opposite charges. This implies all the flux lines leaving one conductor must necessarily terminate at the surface of the other conductor. And these conductors are also referred as plates of the capacitors, and the plates can be separated by free space or a dielectric. So as shown in this figure, here we have two conductors and they are maintained at a potential difference V. The potential difference V is given by V1 minus V2, that's equal to minus integral 2 to 1 E dot dl, where E represents the electric field existing between the conductors. And here we have assumed conductor 1 is carrying positive charges. So this is conductor 1 and this is the second conductor. So what is the capacitance? Capacitance of the capacitor, it is defined as the ratio of the magnitude of charge on one of the plates to the potential difference between them. That is C is equal to Q by V. And we know Q is equal to, as per Gauss's law, Q is equal to psi and psi is equal to integral d dot ds, and that is same as epsilon closed integral E dot ds divided by V, that is a potential difference, that is equal to integral E dot dl. Capacitance, it's a physical property of the capacitor and it is usually measured in farads represented by capital F. And the capacitance can be obtained for any given two conductor by either of these two methods. The first method is assuming Q and determining V in terms of Q, and this involves Gauss's law. We have to apply Gauss's law there. And the second method is assuming V and we determine Q in terms of V, and this involves solving the Laplace equation. So here we will be following the first method, that is assuming Q and determining V with the help of Gauss's law. So what are the steps involved? First, we have to choose a suitable coordinate system. Then consider we have got two conducting plates carrying charges plus Q and minus Q. And then with the help of Coulomb's law or Gauss's law, we have to determine E, and from E we can find the potential difference V is equal to minus integral E dot dl. In our calculations, the negative sign may be ignored because we are interested only in the absolute value of V. So once you have the potential difference V, we can obtain the capacitance C is equal to Q by V. And here the starting itself we have said we already assumed Q, so Q is not to S, and now we determined V also. So we can easily find the capacitance of any given two conductors. Let's apply the method that we just learned to determine the capacitance of a coaxial capacitor and also to determine the capacitance of a two-way transmission line. Coaxial capacitor. A coaxial capacitor is also known as a coaxial cable or a coaxial cylinder. So consider this figure. Consider a length L of two coaxial conductors with inner radius A and outer radius B. So the outer radius B is greater than the inner radius A, and these conductors are separated by a dielectric medium with permittivity epsilon. Here the conductor 1, that is the inner conductor, it carries positive charges, and the outer conductor carries negative charges, and the charges plus Q and minus Q is uniformly distributed on it. So now let's apply the Gauss's law to an arbitrary Gaussian cylindrical surface of radius rho, where the radius rho, it lies between the value of A and B. So this is the value of A, here comes the value of B. So our Gaussian surface, it lies somewhere in between. So what does Gauss's law says? It says the total charge enclosed is equal to flux. So we have Q is equal to closed integral d dot ds, and we know what is d. D is equal to epsilon E, and here we have only one component, that is only rho component present. So substituting in that, we get Q is equal to closed integral d dot ds, that is equal to epsilon E rho 2 pi rho L. And from this we will get E is equal to Q by 2 pi epsilon rho L A rho, because here we have only rho component exists. So once you have the electric field intensity E, we can determine potential difference V is equal to minus integral 2 to 1 E dot dl, that is equal to minus of integral from B to A E. What is the value of E? That is Q by 2 pi epsilon rho L A rho dot dl. The rho L component is d rho A rho, that is equal to, integrate it, apply the limits, you will get it like Q by 2 pi epsilon L ln V by A. So once you have the potential difference V, you can compute capacitance C is equal to Q by V, that is equal to 2 pi epsilon L ln B by A. So this C represents the capacitance of a coaxial cylinder. Second case, capacitance of a two-way transmission line. As shown in the figure, let rho L and minus rho L be the line charge densities of line A and line B. So we have two wires or two lines, A and B. And let D be the distance between the wires. D be the distance between the wires, and R be the radius of each wire. R is the radius. Okay, that is the radius, not the diameter, that's the radius. The electric field between the wires at point P, this is point P, due to rho L is E is equal to rho L by 2 pi epsilon x Ax, and the electric field between the wires at point P due to minus rho L is E is equal to minus rho L divided by 2 pi epsilon d minus x into minus Ax. The total potential difference V is given by, V is, we have to add up the values, that is minus integral B to A E dot dx Ax, that is equal to minus integral from d minus r to r E dot dx Ax. That is equal to, the potential difference is created with the presence of both rho L and minus rho L. So that is equal to minus of integral d minus r to r rho L by 2 pi epsilon x Ax dot dx Ax, then plus because of minus rho L. So that minus comes, we have minus integral d minus r to r rho L by 2 pi epsilon d minus x Ax dot dx Ax. This is equal to, we have rho L by 2 pi epsilon common in both the terms, so that we have taken common, that's equal to rho L by 2 pi epsilon. Then integrating this first equation, that is integral dx by x is equal to ln x. So we have minus this minus ln x, limit varying from d minus r to r. Then let's look at the second term. Integral dx by d minus x is equal to minus of ln d minus x. So that minus and this minus becomes plus. So we have plus ln d minus x, limit varying from d minus r to r. That is equal to, let's just simplify, you get rho L by 2 pi epsilon ln d minus r by r plus ln d minus r by r. So this becomes 2 times ln d minus r by r. So 2 will get cancelled and we will have V is equal to rho L by pi epsilon ln d minus r by r. In practical cases, the distance between the wires will be very much greater than the radius of the wire. So we can consider d minus r is almost same as d. So we have d minus r by r approximately same as d by r. So that the potential difference V will become royal by pi epsilon ln d by r. Initially our expression was like d minus r by r. That will get simplified as ln d by r. So the capacitance per unit length, we know C is equal to, what was the basic expression was C is equal to Q by V. Since this is line charge density, we have C is equal to royal by V farad per meter. This is the capacitance per unit length. Substituting the value for V, we get C is equal to pi epsilon ln d by r farad per meter. So once you know the capacitance per unit length, we can compute the capacitance for a total length of L as C is equal to pi epsilon L divided by ln d by r farads. So C is equal to pi epsilon L divided by ln d by r is the capacitance of a two-way transmission line. So what we learned by this video lecture? We learned continuity equation and we learned how to compute the capacitance of a coaxial cable and two-way transmission line. And for thorough understanding, I suggest all students to go through the textbook Elements of Electromagnetics authored by Matthew N. O. Sadiko. Thank you.